Okay, let's just jump right in. We're going to be unpacking the invisible science that really underpins all of our modern communication. If you've ever looked at a radio tower and wondered how that simple piece of metal, translates a clean electrical signal into a wave that can cross an ocean, then you are definitely in the right place.
Welcome to your deep dive on antenna fundamentals. We're treating this as a really intensive technical review. Our mission today isn't just to, define the jargon. We want to establish the core physics, the essential trade-offs, and of course the key numbers that drive antenna design.
I love that. So if your goal is exam preparation or you're trying to get a handle on high-level system requirements, this is your shortcut.
Exactly.
We're going to move from the absolute basic physics all the way up to these highly complex, high-gain directional systems. I mean, think of the antenna as the ultimate translator. It's the crucial interface between the controlled electrical energy in a cable and, well, the vastness of free space.
And that ability to transmit and receive energy, it all starts with understanding the basic structure. So let's just start with the hard definition. The antenna is fundamentally a conductor or a system of conductors used either for radiating electromagnetic energy into space.
That's the transmitting function.
Right. Or for collecting that energy from space. That's the receiving function.
Okay, so that's the core component, but it doesn't work alone, right? It needs a whole system to get the power from the transmitter out into the air. What are those three essential parts of the complete system we need to think about?
We have to trace the path. So first you have the coupling device. This is the network that matches the impedance of the transmitter to the rest of the system. It ensures you get maximum power transfer.
Fair.
Second, you've got the feeder. We usually just call this the transmission line or the coax cable. It just carries the energy. And then finally, the third part is the antenna itself. And that's where that electrical energy gets converted into the propagating electromagnetic wave.
That whole process makes it feel like a one-way street. Power flows out. But here's maybe the most satisfying concept for designers, the one that makes system modeling so much simpler. It's the principle of reciprocity.
Reciprocity is an absolute cornerstone of antenna engineering. It states that the properties of an antenna apply equally, whether it's used for transmitting or receiving.
As long as you're on the same frequency.
Provided you are using the same operating frequency, yes. So if you spend months optimizing an antenna to be super efficient at sending a signal, you automatically know it's going to be just as good at pulling that same signal back out of the air. It saves so much work.
Let's get into the pure physics of it. How does electrical current just moving back and forth on a metal rod suddenly become a wave moving at the speed of light? What is the actual mechanism of radiation?
It's all about an electrical feedback loop, and it's governed by two fundamental interconnected laws. If you remember these two, you basically understand the cause and effect of how these waves are generated.
Okay, lay them out for us.
Rule 1. A moving electric field creates a magnetic or H field.
Right.
And Rule 2. A moving magnetic field creates an electric or E field.
So they create each other. If I start a current, that creates an E field, which then immediately makes an H field, and that H field makes a new E field, and on and on.
Exactly. They are constantly feeding off each other, propagating the energy away from the source. So the radiated energy has these two components, the electric, or E field, and the magnetic, or H field.
Okay, and there's a critical detail here about their relationship in space, right?
A very critical detail. These two fields are physically perpendicular to each other at a 90-degree angle in space. But, and this is the part people often miss electrically, they are also 90 degrees out of phase.
And that phase difference is what allows them to be self-sustaining. If they were in phase, they'd just collapse.
Precisely. The energy stored in the electric field at one moment is converted to energy in the magnetic field a quarter cycle later, and then back again. This continuous 90-degree shift allows them to combine and produce that single self-propagating electromagnetic wave.
And once that wave is out there, traveling, does it lose power on its own?
No, the total energy in the wave actually remains constant in space. It doesn't just dissipate into the vacuum. The decrease in power we measure at a distance is only due to, well, two things. Either absorption by the atmosphere or the Earth, or more commonly, it's just spreading out over a bigger area. It's the inverse square law.
The energy is the same, it's just less concentrated.
Exactly.
Okay, that's the radiation mechanism. Let's shift to the physical antennas themselves. We need to classify the two basic types, which often comes down to their frequency and their relationship to the ground.
Right, we use two primary classifications. First, you have Hertz antennas, which are also called half-wave antennas. These are generally used for frequencies above 2 megahertz. Think of them as conductors that are typically insulated from the ground.
And for the lower frequencies?
That would be the Marconi or quarter wave antenna. These are for frequencies below 2 megahertz, so your medium and low frequencies. And the key difference is that these antennas are vertical and they're grounded at one end.
So that 2 megahertz line is the big divider for exam purposes.
It's a crucial line to remember.
Let's focus on the absolute building block of almost all RF systems. The half-wave dipole, sometimes it's called a doublet. What's its electrical length?
A half-wave antenna is simply a conductor whose electrical length is exactly 1/2 of the wavelength of the frequency you're using. When we feed RF voltage into it, we excite what are called standing waves along the wire.
Okay, and the geometry of those standing waves is everything because it tells us where to connect our feed line. This is the heart of impedance matching. So what happens at what's called a current loop?
Right, so a current loop is a specific point on that wire. It's the location that experiences the maximum amount of current and at the exact same time, the minimum amount of voltage.
Ah, and since impedance is voltage divided by current, if current is max and voltage is min, that means
You have a point of very low impedance. And on a standard center-fed half-wave antenna, that loop is always right in the middle.
and the opposite condition has to be the current node.
Exactly. A current node is the point of minimum current and maximum voltage. So that results in a point of very high impedance. You'll always find the nodes at the extreme ends of the antenna.
So this creates a critical cause and effect rule for system design. Since the center of the half-wave antenna is a low impedance point, that's almost always where you connect the transmitter.
Yes, we call that the center feed or current feed method. Your transmission line, your coax, typically has a low impedance, maybe 50 or 75 ohms. You have to connect it to the part of the antenna that naturally matches that.
Trying to feed it at the ends at the high impedance point would just be a disaster. Most of the power would reflect right back.
A total mismatch. You'd get almost no radiation. Matching that impedance is rule number 1 for efficiency.
Okay, a quick recap. We've established the basic physics, this idea of reciprocity, the E and H field interplay, and how standing waves create that perfect low impedance spot at the center of a dipole. Now that we know about the internal dynamics, let's look at how we measure the power that actually leaves the antenna. And that brings us to maybe the most important metric, radiation resistance.
Right. Radiation resistance. This is a number every engineer has to know. It's a bit of a hypothetical concept, but it's the critical measure of how successful the antenna is at its job.
Which is turning electricity into space waves.
That's right. So the definition of radiation resistance, or R, is the hypothetical resistance that if you swapped it in for the antenna, would consume the exact same amount of power that the antenna actually radiates into space.
So it's not a physical resistor, it's just a number that quantifies the useful work being done. What is that benchmark number we need to burn into our brains for a perfect half-wave antenna in free space?
The theoretical radiation resistance for that ideal half-wave antenna, far from any ground effects, is approximately 73 ohms.
73 ohms.
73 ohms. That is the design ideal. Now, in the real world, a practical antenna, especially near the ground, will see its resistance vary. But 73 is the gold standard we aim for.
So let's talk about why that number is so important. Why is it so crucial to maximize radiation resistance in a real-world system?
It all comes down to the fight against loss. Any antenna has what we call ohmic resistance.
Yeah.
This is just the actual physical resistance of the metal wire itself, and it dissipates power as heat.
I squared R loss.
Exactly. And the ohmic resistance is usually tiny, maybe 1 ohm or even less. So when your radiation resistance is high, say 73 ohms, that tiny 1 ohm of heat loss is just a tiny fraction of the total power. You're radiating 73 units of useful energy for every 1 unit you lose as heat.
But if the design is bad or maybe the antenna is installed poorly, I'm guessing that radiation resistance could drop.
It could drop dramatically. And if it dropped to, say, 5 ohms, suddenly that 1 ohm of ohmic loss represents a huge chunk of your power. Your efficiency just plummets. So the goal is always to maximize radiation resistance to overwhelm those inherent losses.
Excellent. Okay, moving on from efficiency, let's define antenna gain and directivity. This isn't about creating power, it's about focus.
Right. Gain is purely a ratio of focus.
Yeah.
It's the ratio between the energy propagated in a specific favored direction compared to the energy that would be propagated by a theoretical, perfectly non-directional antenna, what we call an isotropic antenna.
It's the flashlight versus the bare light bulb. A high-gain antenna is just a highly directional antenna.
Correct. And that brings us to the next critical concept, polarization. This is essential for understanding system requirements, especially if you're, say, writing a policy memo about frequency use or planning a network.
So how is polarization strictly defined? What part of the wave determines it?
Polarization is defined exclusively by the direction of the electric field lines of force, the E field.
And we have three main types to define.
We classify them based on how that E field is oriented. We have vertical polarization, where the E field lines are vertical. That usually comes from a vertical antenna. Then you have horizontal polarization, where the E field lines are horizontal. And finally, circular or elliptical polarization, where the E field lines actually rotate a full 360 degrees with every cycle of RF energy.
Okay, now for the critical part, cause and effect. Why does the required polarization change depending on the frequency and the path the wave takes? Let's start with ground wave transmission, like AM radio.
Okay, so for ground wave, where the wave literally hugs the surface of the Earth, you must use vertical polarization.
Must use it. Why?
The reason is simple physics. The Earth acts as a pretty poor conductor at these low and medium frequencies. If you use a horizontal E field parallel to the ground just shorts it out. The signal gets attenuated and dies off very quickly. But vertical E field lines are perpendicular to the ground, so they're minimally affected, and that allows the wave to travel for hundreds of miles.
So vertical is mandatory for low-frequency ground wave. What about high frequencies, where we're intentionally bouncing the signal off the ionosphere skywave?
For skywave, you can actually use either vertical or horizontal polarization at the transmitter.
Why doesn't it matter as much there?
Because the signal's path through the ionosphere, which is a dense layer of charged particles, causes the wave to twist and rotate. By the time that wave arrives back at the receiving antenna, it's already elliptically polarized. The original polarization is basically scrambled.
And for VHF and UHF, your line-of-sight signals.
Since those waves travel directly and don't go into the ionosphere, either polarization is technically fine. The choice there comes down to other more practical advantages.
Let's get into those practical advantages. This is where the policy choices come in. When is vertical polarization strategically the better choice?
Below about 50 to 100 megahertz, vertical often gives you a slightly stronger signal. But the huge, overwhelming advantage is that it provides omnidirectional communication.
It goes out equally in all directions horizontally.
Exactly. Which is critical for anything, mobile cars, planes, ships, that need to communicate without knowing exactly where the other station is.
And the trade-off. When would you prefer horizontal polarization, which is usually above 100 megahertz?
Horizontal is preferred because it's better at rejecting what we call man-made noise. Things like car ignitions, electrical appliances, power lines, they all generate a lot of vertically polarized noise. A horizontal antenna naturally rejects that.
I see.
They're also less affected by energy absorption from things like buildings. And a horizontal dipole has a natural figure 8, or bidirectional pattern, which can be really useful for minimizing interference coming from certain directions.
That's a great summary. We now have that 73 ohm standard for efficiency, and we know that choosing polarization depends on frequency, path, and noise. To really maximize all this, we need to map where the energy is going, and that takes us to radiation patterns.
Right. If we're going to talk about focusing energy with gain, you need a visual map, and that map is the radiation pattern.
What is it exactly?
A radiation pattern is just a graph. It's a plot of the radiated energy measured at a bunch of different angles, and it shows you the direction and the strength of the power distribution, usually in 2 or 3 dimensions.
Let's nail down the difference between the theoretical ideal and what we see in the real world. First, isotropic radiation.
The isotropic radiator is the impossible ideal. It radiates energy perfectly equally in all directions, like a tiny point source in space. If you measure the signal strength anywhere on a sphere around it, the measurement is identical. It's the universal reference point we use to measure the gain of every real antenna.
And the reality is anisotropic radiation.
Yes. Anisotropic just means it radiates energy stronger in one direction than in others. If the isotropic radiator is a bare light bulb, the anisotropic antenna is a flashlight. And almost every antenna we use is anisotropic because we want to send the power where it's needed.
To really visualize that flashlight beam, we need the right kind of graph. We use rectangular plots and polar plots. Why is the polar coordinate pattern the one that designers always use?
A rectangular plot is okay for comparing numbers, but it doesn't give you a feel for the space. The polar coordinate pattern plots the intensity by its distance from the center, which represents the antenna. And the angle around the plot tells you the direction.
So you get everything in one picture.
Instantly. You look at the shape on the polar plot, and you see both the direction and the magnitude, the strength of the radiation all at once. It's indispensable for planning where to put an antenna or predicting its coverage.
And looking at that visual map brings us to the jargon we use for performance. Lobes and nulls.
A lobe is simply the part of the radiation pattern that's covered by radiation. It represents the direction of maximum radiation. We talk about the major lobe, which is the strongest one, and then minor or side lobes, which are weaker bits of radiation going in directions you didn't really intend.
And the null.
The null is the exact opposite. It's an area in the pattern with minimum radiation, ideal at 0, and for system designers, nulls can be just as important as lobes.
Oh, so?
Well, if you know you have a source of interference coming from a specific direction, you can design and orient your antenna to place a deep null right in that direction to cancel out the noise.
Okay, so we've got the map, the pattern, and we know the key terms, lobe and null. Let's apply this geometry now to those two foundational antennas we talked about earlier, the Hertz and the Marconi.
Perfect. Let's start again with a half-wave antenna, the Hertz or dipole. Its physical construction is two separate conductors, each 1/4 of a wavelength long.
For a total of a half wavelength.
For a total of a half wavelength, yes. And critically, they're insulated from the ground and fed right in the center.
And you mentioned its radiation pattern is like a donut. Explain that shape and where the maximum radiation comes from.
That donut, or toroid shape, is its signature. Maximum radiation always comes out perpendicular to the antenna wire itself. The nulls, the hole in the donut, are off the ends of the wire.
So if I mount that dipole horizontally, the power goes up, down, and out to the sides.
Right. And if you mount it vertically, the maximum radiation goes out equally in all horizontal directions. Yeah. And that gives you that perfect omnidirectional pattern we were talking about earlier.
And just to reiterate, the feeding method is always center feed.
Always. Because that's the low impedance, high current point.
Okay, now for its shorter sibling, the quarter wave antenna, the Marconi, it's physically only a quarter wavelength long. So how does it become resonant if it's only half the required length?
This is where the really clever concept of the image antenna comes in. The Marconi design requires one end of the conductor to be grounded. The ground itself acts as an electrical mirror. It provides the missing quarter wave section, creating a virtual image of the antenna underground.
So the grounded quarter wave antenna acts electrically just like a full half-wave antenna floating in space?
That's the idea.
Wait a second. If the ground is a mirror, does that mean it's radiating power into the ground? That seems really inefficient.
That's a great question, and a really common point of confusion. It's not radiating into the ground and losing power. The image antenna is a concept that helps us understand the current distribution. It forces that high current point, the loop, to be right at the base of the antenna, which is where you connect your low impedance feed line. The actual wave reflects off the conductive ground and combines with the direct wave to form the final pattern, often pushing more energy toward the horizon.
Ah, so it's essential. But what if the ground is bad? Like if you're installing it over sand or rock?
Then you have a problem.
Yeah.
That poor ground acts like extra resistance and kills your efficiency. To fix this, we use things called ground screens or counterpoises.
Okay, what are they?
A ground screen is just a network of wires buried a foot or two under the surface in a radial pattern. It creates an artificial, highly conductive ground plane right where you need it.
And the counterpoise?
A counterpoise is for when you can't bury wires. It's an elevated system of wires, often just above the ground, that acts as the bottom half of the antenna. It provides that artificial ground and the equivalent of that missing quarter wavelength.
Right. Lastly, for this section, we need to talk about antenna loading and tuning. In the real world, you can't always build an antenna to the perfect physical length. Why do we need electronic tuning?
It's all about achieving resonance. If the physical length is even a little bit off, the antenna presents a reactive impedance to the transmitter, which causes power to be reflected back down the line. We use what's called lumped impedance tuning to electronically adjust the length and get it back to pure resonance.
So these are the rules. What if I'm on a ship and my mast is just too short for the low frequency I need to use?
If the antenna is too short, it acts like a capacitor. It exhibits capacitive reactance. To cancel that out and make it resonant, we have to add an inductor, a loading coil in series. This effectively lengthens the electrical path.
And what's the downside of using a big loading coil to make up for a short antenna?
Well, that coil is another component with its own ohm resistance. So while you achieve resonance, a very large loading coil can introduce a lot of loss and really hurt your overall efficiency. You're trading physical size for efficiency.
And if the antenna is too long?
If it's too long, it exhibits inductive reactance. And we compensate for that by adding a capacitor in series to electrically shorten it.
Okay, that makes sense. We've mastered the single elements, the dipole and the Marconi, and we know how to tune them to hit that 73 ohm target. But a single element can only be so focused. To get really high gain, we need to make them work as a team. And this is where we get into arrays.
Right. Time for a whole new level of control.
This section has a lot of new vocabulary, so let's start with the big definition. What is an array?
An array is just a combination of half-wave elements that are all operating together.
Mm.
And the goal is always to increase the overall system gain and directivity compared to what you could get from just a single element.
We need to classify the players in the array. The basic component is the element. How do we distinguish them based on how they get their power?
There are two categories. A driven element is connected directly to the transmission line. It gets its power right from the source. It's the heart of the array.
And the other type is the parasitic element.
All right, and the parasitic element is really a marvel of efficiency. It's not wired up at all.
It just participates.
It just participates. It's not connected to the feed line. It gets its energy purely by electromagnetic coupling. It listens to the driven element and then re-radiates that energy. It just has to be close enough, usually within a quarter wavelength or so.
And the two types of parasitic elements are critical because they determine the direction of the whole array. First, define the reflector.
A reflector is placed behind the driven element, and its job is to act like a backboard. It pushes the radiation forward away from itself. To do this, it's tuned to be electrically a little bit longer than a half wavelength, specifically about 5% longer than the driven element. That extra length adjusts its phase so its radiated signal cancels out the driven element's signal in the backward direction.
And the director.
A director is placed in front of the driven element, and its job is to help focus the energy forward, adding gain. To do that, it needs to be slightly shorter than a half wavelength, about 15% shorter than the driven element. That makes it capacitive, which adjusts the phase to create constructive interference in the forward direction.
It's just amazing that a 5% or 15% change in length can totally change the direction of the power flow, and the performance metric for this is the front-to-back ratio.
Right. That ratio is a key measure of how good the antenna is. It's the ratio of the energy radiated in the main forward direction compared to the energy radiated in the exact opposite direction. You want a very high front-to-back ratio. It means you aren't wasting power and you're rejecting noise from behind you.
So all of these directional patterns come from controlling the phase and spacing between the elements, which causes reinforcement in some directions and cancellation in others. Let's look at the two main types of driven arrays. First up, the broadside array.
The broadside array is designed to shoot energy perpendicular to the line of the array. It's inherently bidirectional. It radiates equally in two opposing directions.
And how is it set up?
The elements are placed parallel to each other, and they are all fed in the same phase.
And the pattern.
Maximum radiation develops in the plane that's at right angles to the axis of the array. Imagine a line of vertical antennas. The energy shoots out horizontally from both sides of the line. Okay. You get the best gain when the elements are spaced about 0.65 wavelengths apart.
Okay, next is the end-fire array. This one is designed to shoot energy along the line of the array itself.
Exactly. The end-fire array aims for maximum radiation along the axis of the array. The elements are still placed parallel to each other, but the crucial difference is that they are fed 180 degrees out of phase.
So that's the key. The phase relationship determines the pattern. Same phase gives you broadside or perpendicular. 180 degrees out of phase gives you end-fire or axial.
That's the cause and effect summary for driven arrays. It's all about phase and spacing.
We've established how to use phase and spacing to control direction. Now let's look at how engineers specialize these arrays, stacking them or adding those parasitic elements to get the extreme gains we need for modern communications.
Right. Let's start with collinear arrays. This is basically just stacking dipoles end to end. What's the mechanism here?
Well, the arrangement is key. You have multiple half-wave elements arranged in a straight line, and that they're all connected so their currents are kept in the same phase along the whole structure.
And the benefit of doing that.
The pattern is still that familiar donut shape of a single dipole, but the gain is much higher and the beam width is much, much narrower. Adding more elements sharpens the beam, focusing the energy into a smaller area.
What's the limit? Why not just stack 100 of them?
You run into efficiency problems. As you add more elements, the ones at the far ends start to get less current and their phase can shift a bit. This leads to losses. Optimal spacing for the best gain is usually somewhere between 0.4 and 0.5 wavelengths apart.
Got it. Okay, next up are the parasitic arrays, where we combine that driven element with reflectors and directors for extreme directivity.
Right. And the performance of these arrays, like the reflector being 5% longer and the director being 15% shorter, it all depends on that precise tuning and placement, usually about a quarter wavelength away from the driven element.
Let's focus on the reflector again for a second. How exactly does it push the energy away?
The induced voltage in the reflector is slightly inductive because it's long. This causes its re-radiated energy to be out of phase. The total effect is that its signal is 180 degrees out of phase with the driven element signal on the backside, which leads to cancellation there.
And the most famous example of this kind of array is the Yagi antenna.
The Yagi is everywhere. You see it on rooftops for TV reception. It's a highly directional antenna, usually with one driven element, one reflector, and then one or more directors all lined up.
What's the major design trade-off that a planner needs to think about when they're specifying a Yagi antenna?
It is the classic gain versus bandwidth trade-off.
No.
The more parasitic elements you add, the more gain and directivity you get, but you also get a much, much narrower frequency response. The bandwidth shrinks. If you add too many directors, the antenna becomes incredibly sensitive to the frequency. Adding one director might get you another 2 dB of gain, but you pay for it by having to operate in a very tight frequency range.
So they're great for fixed links, like TV or deep space communication, but terrible for anything that needs to be broadband.
Exactly. Now, moving on to antennas that are designed for wide frequency operation, let's talk about long wire antennas. What's the definition?
A long wire antenna is just any antenna that is a wavelength or longer at its operating frequency. They're fundamentally different from the resonant half-wave antennas we've been talking about.
And a famous specific type is the beverage antenna.
The beverage is a single wire, usually 2 or more wavelengths long. The crucial detail is that it's terminated at the far end with a resistor that matches its characteristic impedance.
And terminating it does what?
That termination makes the antenna non-resonant. It suppresses reflections from the end of the wire, which makes it operate over a huge range of frequencies. It's truly broadband, and it makes it highly unidirectional.
The highest development in this class, and one that's a big deal for fixed global communications, is the rhombic antenna. It's shaped like a diamond.
The rhombic is the workhorse of long-distance HF communication. It's 4 conductors in a diamond shape, and just like the beverage, it's terminated by a non-inductive resistor.
What are the main advantages of the rhombic that make it so popular for system planners?
The strengths are both logistical and technical. First, its broadband characteristics mean it can operate over a very wide frequency range without needing to be retuned. That's a massive operational plus. Second, it's not very critical when it comes to adjustment, which makes it incredibly easy to build and maintain compared to a finely tuned Yagi.
But all that performance and flexibility comes with one giant logistical trade-off, which often dictates the whole business plan, and that's real estate.
Exactly. The number one disadvantage of the rhombic is the sheer amount of land it requires. The legs of that diamond often need to be 1 or 2 wavelengths long at the lowest frequency. For low HF, that can mean several hundred feet of wire and towers. You need a massive, dedicated site.
We've covered the theory, the geometry, and the complex engineering of these arrays. Before we wrap up, we have to pivot to the non-negotiable safety considerations that come with generating and focusing this much power.
Right. High-power RF fields pose some serious and often invisible risks. What are the 2 major hazards technicians need to be aware of?
The 2 categories are direct contact and energy absorption. Direct contact causes RF burns.
And these aren't like normal burns.
No, they're particularly dangerous because they are deep, penetrating third-degree burns that happen when current is induced in your body from touching an energized line or antenna. They can be much more serious than a thermal burn.
And the second, more insidious hazard is internal heating.
That's right. It's called dielectric heating. This is the heat that results from internal losses when human tissue, which acts as a dielectric material, is placed in a strong RF field. The rapid reversal of your molecule's polarization causes friction and internal heat.
This sounds especially bad for organs that don't have a lot of blood flow to cool them down. What's the critical field strength number that defines a high-risk area?
Vital organs are very susceptible. The RF field strength right near a high-power antenna can easily exceed the hazardous threshold of 10 milliwatts per centimeter squared.
10 MBCM hertz.
That is the official high-risk zone where prolonged exposure can lead to internal organ damage, especially to the eyes, which can't dissipate heat well.
And beyond the biological risks, RF can be a hazard to the environment and equipment too, right?
Absolutely. The energy can be high enough to generate heat or induce current in ungrounded metal objects, even just a tool or a piece of scaffolding, and cause a spark. This can ignite combustible materials or, in a military setting, even detonate ordnance by inducing a current in its firing mechanism.
So what are the absolute non-negotiable safety guidelines for anyone working around these powerful systems?
The number one rule is the established safety protocol: lockout, tech out. If you're working near a rotating antenna, the power source has to be locked open and tagged before anyone goes near it. And the general rules are just common sense. Obey all the warning signs, keep a safe distance, and never ever rely on your own judgment. You have to use proper instruments to measure field strength. Never assume you're safe just because you're a certain distance away.
We have successfully come full circle, from the microscopic mechanism of radiation all the way to these massive array systems and the safety protocols they require.
To synthesize the core knowledge, everything relies on that concept of one-half wavelength resonance and the standing waves that gives us those predictable loopsmax current low impedance right at the feed point.
And performance is characterized by maximizing radiation resistance, aiming for that 73 ohms against the ohmic losses. The choice of polarization is a critical trade-off. Vertical for low-frequency ground wave and omnidirectional needs. Horizontal for high frequencies to beat man-made noise.
And finally, any complex, high-gain communication requires the precision of arrays. We get that directionality by manipulating the phase and spacing of multiple elements. And we always have to remember the key constraints: the gain versus bandwidth trade-off you see in a Yagi, and the logistical constraint of real estate that you see with a big, effective rhombic antenna.
It really all comes down to precision. We saw how the tiny difference between a parasitic element acting as a reflector, just 5% longer, and a director 15% shorter, can completely shift the direction of an electromagnetic wave.
That extreme sensitivity is really what's so amazing. It highlights how critical those physical dimensions are to the wave's behavior.
And that extreme sensitivity leads us to our final provocative thought for you to consider. If maximizing performance rests entirely on maintaining this incredible precision, and if fixed metal conductors inherently limit our ability to tune rapidly across a wide frequency range, then what happens next?
Where does the technology go?
The future of antenna tech is looking beyond static pieces of metal. Imagine using advanced materials that can dynamically and instantaneously change their electrical length or phase profile without any moving parts. This would allow true, real-time, adaptive beam steering that could maximize a signal on the fly, responding to changing atmospheric conditions or new sources of interference in milliseconds. This blending of precision physics with dynamic material science, that's where the next real breakthroughs are going to be.
A fascinating area to explore as you continue your studies. Until then, keep digging into the details.
Happy learning.